Yes, we can
Okay,
see.
great. Okay, so thank you for Guo's nice presentation. So I will try my best to finish like 10:20. Okay, I will try my best to finish before 10:20. So so thank you for the invitation from IPN 2022. So today my topic is about simultaneous localization and mapping technologies. Okay, for the indoor positioning. So I'm Dr. Song Wen. Currently, I'm a research assistant professor from Hong Kong Polytechnic University at the Department of Aeronautical and Aviation Engineering. Okay, so currently I'm also a member of IEEE and a member of ION, which are the two popular society for the navigation research. So before I start, I wish to use several seconds to introduce myself. I get my PhD degree in 2020, by the end of 2020, in mechanical engineering of Hong Kong Polytechnic University. And during my PhD, I was a visiting researcher in UC Berkeley with a special focus on the navigation for autonomous driving. And after that, I was a senior research fellow, okay, postdoc also in the same university in Polio. And from 2021, I was become a research assistant professor in the Department of Aeronautical and Aviation Engineering. So in the past about 7 years, my research focus is navigation for autonomous systems, such as using the SLAM technology, which is also applicable to the indoor positioning. For example, SLAM technology based on the vision and camera and LiDAR can also be used for the indoor positioning. So in the past about 7 years, I get some paper publications and conferences and session chair in the Navigation Society. And specifically, I have several years of research experiences with biotechnologies. And okay, here's some photos about my past research experiences. So let's start. So my presentation in the tutorial is going to include 3 parts. Okay, the first one is going to mathematically introduce the essence of simultaneous localization and mapping. So I will start from the GPS. Okay, so as a comparison with the SLAM, because the GPS is one of the most popular technology in the navigation society. Okay, it's easier to understand. And then we are going to have the mathematical description of the SLAM problem, how we can formulate the SLAM problem in a probabilistic view. And the second part is the very popular visual SLAM. Okay, I think majority of you guys in the navigation research may know this newly developed popular technology. And I'm going to introduce the overview and several key parts, which is going to be very important to get the location based on the visual SLAM. Several technology, for example, the feature detection, checking, and epipolar constraint to recover the motion. This is going to recover the depth of the features. And then we are going to introduce the integration of the visual with the illusion to mitigate several drawbacks of the visual, solely based visual solutions. The last one is the LiDAR SLAM. Okay, it's going to introduce the similar to the visual SLAM. We are going to introduce the feature extraction, for example, based on the NDT, the normal distribution transform, and the count of popular solutions based on the age and planar features. And finally, we are going to introduce the observability and degeneration cases in the SLAM problem. So this is the 3 outline, 3 subtopics of the tutorial. So first, we look into the GPS positioning, as Dr. Zhang had mentioned slightly just now. So for example, we receive the signals from the satellite. For example, we receive the satellite signals from at least 4 satellites. We can get the location. For example, in here, okay, the signal is from Z. Okay, this is the typical least square estimation problem. For example, in here is the measurement. For example, we get the shoot range. This is the distance from the receiver to the satellite. Okay, we can construct the observation vector Z. So for example, this is the range measurement. Okay, it includes the range distance between the receiver and the satellite. And this is the geometry matrix of the satellite to the receiver. So this is some kind of observation function, or sometimes we call it the Jacobian matrix in the estimation theory. And by doing the least square iteration, we get the state. This is what we want to estimate. Okay. And following this slide, we are going to use the blue to. Sorry. Something wrong with my Apple Watch. So based on the least square estimation, so in the following slide, we are going to use the blue variables to denote the non-variable, for example, observation and the edge, and use the red annotation to represent what we are going to estimate. So for the simultaneous localization and mapping, from the formula you can find it tries to estimate the location of the agent and also estimate the surrounding map simultaneously. That's why it's called simultaneously localization and mapping. So it's going to estimate constructing a map. Okay, let's see the first step, and simultaneously keep checking of the agent location. So for example, this is a very famous figure from Dr. Udo. Okay, in here, okay, let's see the robot and there is a camera installed on the top of the system, and it tries to check the landmarks on the ground. Okay, and based on those observations from landmark, it can estimate the trajectory. So trajectory means you get a location. By accumulate those locations, you get a trajectory. And based on those sparse landmarks, okay, those are the observations. So by recover the observation, by recover the location of those landmarks, okay, we can get a sparse feature map. Okay, this is the map, this is the location. So this is called visual system. Okay, how it looks like. So differently, the visual-based method is sense the environment with the camera image. Okay, this is called visual SLAM, called visual simultaneous localization and mapping. So for different, if we get a LiDAR, we can use the LiDAR to sense the depth directly. So for a camera, it can only obtain the visual scale, only obtain the 2D pixel location of the feature. For LiDAR, it's more straightforward. Okay, it can directly get a location based on those depth information. So we can get the map simultaneously based on the generated, based on the estimated locations. By accumulate those point clouds based on the estimated location, we get the map and the location simultaneously. So this is the two most popular solution in the SLAM society. So if we look into the mathematical description of the SLAM problem first, okay, what we have, okay, what we have is a set observation. For example, this is the visual or LiDAR. O means observation from epoch 1 to epoch t+1. Okay, this is the observation. So that is the control input. For example, this can be a LiDAR. This can be, for example, we get odometers. You can get a control input, or sometimes we call it a relative motion. So based on those two parts, we try to estimate the posterior of the state and the posterior of the map. So this is the general probabilistic view of the SLAM problem. So this is what we have. This is what we want to estimate. We try to model this problem in the probabilistic view to estimate the posterior, to maximize the posterior real probability of this term. So if we divide this part to two sections, so the first is we try to estimate the location. We are going to do this, okay? By doing the rearrangement of this posterior estimation term, we get, okay, so in here is the state in the previous epoch, in the current epoch, and the control input together with the map. Okay, based on assumption, we already get the map and we try to estimate the location. Okay, this is the posterior of the observation. So all those first are the prediction of the state, because we can have some connections between the current state and the state from previous epoch. So this is the posterior form. So for the mapping, it's almost the same. So this is what we have in the previous epoch, kind of prediction of the current epoch. And in here is the state. This is the map in the previous epoch, and the observation can control input. Okay, and then you can get the posterior of the map in the current epoch. So we are going to divide this general form into the two parts. Okay, first we try to estimate, try to maximize the posterior of the current state estimation, and we try to maximize the estimation of the map. Okay, the posterior of the map. So the typical solution for the SLAM problem includes, for example, the common filtering and the mono-SLAM. If you want for the most old, but one for the most popular solution, most famous, not most popular. It's the most famous solution for the visual monocular SLAM. Okay, it's in 27 And the second one is the filtering base. For example, we can use the multiple particle filtering for the two-dimensional LiDAR system, such as the G mapping in 27. Okay, those are the two typical solutions: Kalman filtering for the visual and particle filtering for 2D. And okay, in short, the LiDAR and the visual are the two key categories. So in short, okay, let's see the general form. What we have is the observation. What we have is also the control input from, for example, we get an odometer, we got an IMU, we can get the U means the control input. We try to maximize the posterior of risk probability of the map and the state estimation. So based on the rearrangement, we can get to sub-optimal solution for the map and localization. So this is so-called the simultaneous localization and mapping. So if you look into the key pipelines of the camera-based solution, so what we have is a camera. We can get the image to do the feature detection. So why we need to do the feature detection is that if we directly process all the pixel information from image, it can be quite time computational load. Okay, if we extract the represent features, for example, here's the H feature. If we only use the represent features, it can be more efficient. And then we need to do the feature tracking to find out the same feature from consecutive epochs of image. So finally, it's based on those feature pair. Sometimes we call it correspondence to do the feature association to optimize the pose of the image. Try to estimate the relative motion of the consecutive frames of image. So several key steps are required. The first is how to do the feature detection. The first one is the Thomas. Okay, let's say it's quite efficient. Although it's old, but it's efficient. So the second one is do the feature tracking. We try to find out the same feature from two epochs. For example, let's say the first feature. The feature one in the first epoch, in the epoch time, in the epoch T, and this is the second feature. The same feature, but in a different time epochs. Okay, let's say the objective of the feature tracking. And the epipolar constraint, the objective is to estimate the motion of the two images based on the feature tracking result, based on the correspondence. And last one is tries to estimate the location of the features in 3D. So let's say it's corresponding to the localization, and let's corresponding to the mapping. So let's corresponding to the visual system. Okay, let's say it's the localization, let's see the mapping. Okay, the two paths make up the simultaneous localization for the visual. So one of the key features is that only the relative motion can be obtained, can be estimated from the visual system because it's a direct reckoning process. So first, okay, we are going to introduce how we can do the feature detection. But before that, we quickly go through the visual pinhole projection model, how the features are projected into the pixel, into the image plane. So in here is the feature, sorry, here is the feature in 3D represented in the camera frame, okay? In the camera frame in 3D. And its unit is emitters. And based on a pinhole model, we can project this feature into the image. So in here is the image, and the pinhole projection model is like this. Okay, this is the scale function, FU and V to scale the 3D information into the image one. And this is the offset corresponding to, because it's projected in the center, into the central coordinate, we need to offset this term into this coordinate. Okay, so this is the projection of the 3D feature X to the pixel domain. Okay, the unit of this two term is in the units of the pixels. So we can rearrange this equation into the matrix form. This is the location of one feature. For example, the feature C, by project it to the image plane based on this coordinate, we can get a location, and this is the depth. Sometimes we call it the scale. So the depth is defined from this point to this point. Okay, this is the depth this is the component in a Z direction. So this is sometimes called intrinsic parameters or intrinsic metrics. And this is the location of the feature in 3D. So this is the intrinsic, this is the scale, or sometimes called depth. This is the location of the feature. So let's say it's the matrix form, let's say the intrinsic matrix, let's say location is 3D, and let's say the pixel location is a scale. Okay, those are the key steps. Okay, and they say it's redefined as corresponding to a scale and or sometimes called depth. So first about the feature detection. So as I mentioned just now, we need to try to extract the quite representative features to represent one image to guarantee the efficiency of the visual system. So for example, in here, those edge features are dominant. They are quite distinct corresponding to this feature. And by detecting those features are almost enough to use this image. So first, for example, in here, okay, we get a feature over here, the image. First, okay, let's see the location of this feature. By calculate the angel, by calculate pixel value differences. Okay, how this pixel value is distinguished between the neighboring pixel values. Okay, here is the neighbor. UV means the neighbor offset. Okay, and let's say the weighting for each pixel. Okay, in short, the physical meaning of this equation is trying to estimate the weighting sum of a great difference. So secondly, we can do the first order of pair expansion of this equation. So this is the location pixel location value, and let's say the this is the first order term. For example, in here, this is the gradient, U is the offset, and this is the gradient of the y direction corresponding to considering the pixel values. So we can do a rearrangement. Okay, let's see what we have from this equation. And secondly, we can do a rearrangement by calculating the square. We are going to get a matrix form of this equation, okay, to this one. So in here, this is corresponding, the physical meaning of this term is corresponding to how the great difference of the pixels within this feature is distributed. Okay, then we can extract the M matrix. Let's say the weighted distribution matrix by multiply this term with this term. Okay, this is called M matrix. For example, let's say the neighbor and the size of a row is 10 by 10. Okay, we are going to have 100 pixel locations within a neighbor, and this is going to summation is going to 100. Okay, and we get a matrix. Then we can do the SVD decomposition to extract the key or the major directions. Okay, in here we can get we can get two eigenvalues because this is a 2 by 2 matrix. By doing SVD, we can get two eigenvalues, and if both of the eigenvalues are larger than the predefined threshold, it means in both direction we have distinct pixel location, we have distinct pixel grade differences. It means this potentially can be a sharp feature. For example, in here, it can be a sharp feature. For example, if a point is over here, of course, the eigenvalues of this one should be already very small. For example, like 0.1 or 0.2. So this will not be detected as a feature. So see, the Thomas feature detector is very efficient. Only a SVD decomposition is required, and a simple calculations. So that's why it's widely used, because it's efficient and effective. So in here, definitions as I mentioned just now, okay. So after you find, okay, this is a typical features, or sometimes it's a represent feature. What you need to do next is to do detection, to do the checking, okay. Just after the detection, for example, here, okay, let's say the same feature is move over time and we get the trajectory of the feature. So the optical flow to check to the feature checking is based on three assumptions. The first one is constant brightness. For example, the feature in the two image should have a similar brightness. And second one is the short distance. The image differences. The parallax between two images should be small. And the spatial consistency is okay. For one feature, the optical flow, the velocity of the pixel value within the neighbor of this feature should have a similar movement. The speed should be almost the same. So we can do the similar thing. Let's see the entire expansion of a given pixel location. Okay, let's see the gradient. Let's, for example, in here, okay, let's see the gradient of the pixel value. Okay, concerning the pixel location. Okay, you can do the same thing. And also this is for the time, the gradient difference concerning the time, you can get the matrix form. Let's say the motion difference, sometimes we call it the movement of the feature into image. And this is the gradient. And finally, we can write this movement, the movement estimation in the least square form. And A is the observation function, very similar to the one from GPS. And this is corresponding to this one. And we can estimate this one by solving this square iteration iteratively. And finally, we can calculate the movement based on those three assumptions. Okay, so kind of it's very straightforward, and because only solving the least square estimation is required, so the optical flow is very efficient. Also, another method is to using the descriptors to matching the features. It's kind of slightly more time-consuming, but due to the time limitation, I'm not going to introduce the descriptor-based method to do the feature tracking. So in short, what we needed is the feature location of the feature in the first image, and we are going to use the optical flow to estimate the location of the feature in the second image. Okay, this is the objective and the key process of the optical flow. So after you find it's a feature, and you found the same feature using optical flow, so next step is to use the epipolar constraint to recover the motion of the two camera. Okay, for example, use the optical flow to identify, okay, it's the same feature in two images. Okay, so in this slide, I'm going to introduce how to use the epipolar constraint to estimate the motion, the R and T. R means the rotation and T means the translation. So first, okay, let's say the definition of the pixel location of a given feature. And here is a, okay, let's say location. And let's say the location is 3D. And let's say it's in a 2D, pixel domain. And then what we want to estimate is the rotation. This is a transform matrix. This is a typical transformation matrix, including the location and the transformation. And this is the camera intrinsic matrix, as I just mentioned in the definition of the camera projection model. So the objective here is trying to estimate the relative motion, includes the this is actually the transformation, includes the rotation and the translation. Okay, given several feature pairs. So in here, only one feature is demonstrated. Actually, you need several feature pairs to recover the motion of the camera in two frames. So let's take a look how this is happen. So first is the pinhole model. This is the location of the feature in the 3D based on the projection. Based on projection of the intrinsic matrix, we can get the location of the pixel in the feature in the pixel domain. So this is the depth of the feature. So by transformation matrix, you can get this one. Okay, this is the location of the feature in 3D in the epoch T. So based on the rotation and transformation, based on rotation and translation, we can get the location of the feature in the next epoch. And this is what we want to estimate. So by measurement from feature tracking, this is from optical flow, we can get the location of the feature in the next epoch based on the feature location in the previous epoch plus the optical flow. And the next we obtain the model. Okay, this is the most the layman language. Okay, here is the scale, and let's see a location of the feature in the pixel domain from next epoch, and this is the intrinsic matrix. By doing the transformation, we get this one. So this is what we want to estimate is the rotation and translation. Okay, this part is the same. The projection model, the epipolar constraint is the same. We want to estimate the rotation and translation. Okay, the red part. So by doing a substitution using the linear algebra, you can get this term. Okay, don't worry. For in the following slide, we have one slide to formulate this one. So based on this one, we can estimate the rotation and translation based on this matrix by 8 features. Okay, we can directly estimate the R and T based on 8 features. Okay, let's see the from current epoch, pixel observation in the previous epoch, and let's see the same. Let's say intrinsic matrix. So those are known variables. So we can solve this equation to get the translation and notation simultaneously. So, okay, let's take a look how this equation, how this linear algebra is obtained step by step, okay? So first, okay, let's see what we have. And this linear algebra is going to obtain based on this equation, okay? This is the scale of the feature in the epoch t plus delta t, and this is pixel location. Okay, by plus this one. Okay, by doing arrangement, you can get this far. Okay, just multiply this into this term and this term. And secondly, we can multiply a k to the both side. Okay, let's say the scale. Okay, the scale of, okay, we call it, okay, let's say the next epoch, let's say the current epoch, and multiply this into this one, you can get the kt and this term. And in next step, because let's say the scale, we can remove this term into this here. And let's by multiply the inverse of the intrinsic matrix K inverse to the both side. Okay, we can eliminate this term. We can eliminate the K. Okay, so this is the same. This K is eliminated, and this can be rearranged to the left side because this is a scale variable. This is a scale variable. This is a scalar variable, and also we can multiply the t square symmetric operation to the both side. And secondly, we can get this term. And in here, because this is scale, okay, this is scalar, we can move this part to the left side. And finally, okay, because this part and this part is the same, by doing scale symmetrics, we can find, okay, this is orthogonal with each other. This one and this one is orthogonal. It means this part is equal to 0 because they are orthogonal. By doing the multiplication, they should be 0. So in here, corresponding to this should be 0. And then we get this one. This is corresponding to what we want to get in the previous epoch. Okay, let's see what we want to get. So finally, we can already obtain this term. Okay, this term can be used to directly solve this part because those are known variables, and in here are known variables. We can solve it directly. Because this is scalar, we can multiply this one into this in the right side, and we can eliminate this scalar variable. And let's see what we want to get in the previous slide. So finally, you can solve this using an 8-point algorithm. So if you look into the illustration, so based on the feature pair, for example, in here it's 4 features. Actually, we need at least 8 features to solve the problem to get the rotation and the translation. So here's the demonstration. If we accumulate all those motions simultaneously, we can get the trajectory of the visual stand. Okay, let's see the major concepts of the visual stand to estimate the motion based on epipolar constraint. So the next part is actually we have finished the location problem. So next part is to get the map, to get the feature map. So this is the map is made up by the sparse features. For example, the feature, the Thomas feature we have estimated, we have detected and checked in previously. So therefore, we need to recover, okay, the depths of the feature in 3D. So what we done is like this, okay? What we have over here is the camera motion. So based on the previous slide, you can estimate, you have recovered the motion of the 2 images. So it means, for example, in here, the motion R and T is already a known variable. Okay, and the pixel location in 2D is also a known variable. So what we want to do is to estimate, okay, what is the depth? What is the depth? Okay, so let's start with this equation. So let's see the transformation from previous epoch to current epoch. Okay, let's see the pixel location of the feature in the next epoch. Also, okay, current epoch, and let's see the previous epoch, and let's see the intrinsic matrix. Let's see the scale, or sometimes called the depth, and this is the translation. Okay, let's see what we know. And what we want to estimate is the red part. We want to estimate the depth. Okay, and let's see the transformation. And okay, let's extend. Let's see the inverse transform. Inverse transform. Let's say it's corresponding to location of the feature. Let's say corresponding to location of feature in the previous epoch, and let's say the location is ready. Okay, therefore we can based on this, we can get this form. Okay, let's say the scale corresponding to depth we want to estimate, and by multiplying this part, okay, to both sides, we can get this one. Because this is a score symmetric operation to itself. Okay, so therefore that should be 0. This equals to 0 means okay, this part is equals to 0, and this equals to 0. And those are the known variables, and we can directly get the scale we want to estimate. So let's see how it recovers. So let's see the triangulation. Let's see the typical, very typical solutions in the like in the positioning or something. So far we have already estimated the motion differences means the location, and this is the going to estimate the location of the features. So-called the simultaneous localization and the mapping for the features there. So in here is some demonstrations. For example, the ORB3. So this is one of the currently most popular solutions for the features there. So there's a direct method based on the image, and one of the limitation. So actually it gets several limitations. For example, is the camera is always be very sensitive to the illumination conditions, and one of the key problem, especially for the indoor, for outdoor, the dynamic objects, is because the visuals it relies on the assumption that the feature is static. For example, in here the dynamic object can lead to the dynamic features. So one of the solution is to integrate the camera with the IMU. Okay. So time seems to be up. Okay, I will try to finish the response in 10 minutes. So as I mentioned just now, the camera extends you to the illumination and the dynamic object. So the IMU is usually try to integrate to help with the visual navigation with the visual system. So we can get the VINS, the visual inertial integrated navigation. So okay, so the first here is the pipeline, the key pipeline of the visual inertial integrated system. So in here, this is the pipeline for the camera-based system. So in here is how the IMU is modeled. How its IMU is modeled by integrate the IMU with the visual can get optimized state information. So in here is the vectographic model. So for example, here, let's see the state we want to estimate. Usually it includes the position, rotation, and if we get the IMU, we can get the velocity and the bias of a just group and accelerometers. And in here is the features. You can get the projection of the features in multiple frames. And also in here, we can estimate the bias of the IMU. And by solving this vectograph model, we can do the visual inertial integration. So in here, several terms. So by solving this, we have the marginalization. This because of the slide window optimization. This is the state marginalized out within this slide window. So in here is the IMU pre-integration. So in here is the pre-integration procedure. So putting via slide to show us. And this is the covariance metric corresponding to the pre-integration of the IMU. And here is the camera projection. How the image feature is going to construct the state from multiple epochs. Okay, so I still tries to estimate the position and the map. It's the same as the visual system. The major differences is that IMU is used to help with the scale estimation to increase the robustness of the visual system. And for the first part is the visual. For the first part is the IMU modeling. So while pre-integration is required. So because of the high frequency of the IMU, so if you integrate all the high frequency IMU in the FGO in a vectograph, it's going to increase it's going to be quite computational, high computation load. So one of the solutions is to use the pre-integration technique to integrate all those measurements into one single vector. one single factor. Okay, for example, in here, it's going to be 5 factors can be integrated into one factor. So the objective of the pre-integration is to maintain efficiency. So, for example, if we integrate all those measurements, okay, we can have the increment of the position. This is very straightforward. This is the continuous integration of the acceleration. Okay, we can get by doing a double integration, we can get the increment of the position. Based on just scope, based on just scope, we get the increment of the orientation in between the two epochs. Okay, in here is the velocity integration based on accelerometer. So finally, we can formulate a residual based on the observation. This is corresponding to the observation, and this is the state prediction. So this is the residual term corresponding to the mu, and here is the modeling of the mu, includes the true value and the gravity and the bias noise. And this is angular velocity, bias together with the noise. And in here is the projection model. It's kind of very straightforward. So the projection model is tries to project this feature from this image back to previous image, because you will find the same feature in two images. So this is how the constraint from the feature is constructed. And in here, this is the projection model. This is the feature in the previous epoch, for example, epoch J, and this is the predicted feature location in epoch J, and this is the observation. So in here is the typical observation. So due to the time limitation, and we are not digging into this equation. So finally, we can formulate the projection model of this. For example, in here is a projection from very image location. By do a set of location transformation, we can get its prediction location. Okay. Finally, we can do the minus. Okay, still due to the long limitation, I may not dig into this equation. If you get interested, you can refer to a paper. And okay, let's see the how the feature location is projection is constructed. Okay, let's quickly go through the LiDAR-based how to infer the position and the map from Pancora. So the input is LiDAR, and we can do the feature extraction, association, and then we can do the linear optimization. So first, because the Pancora map is quite dense, we also do the same thing to extract the features from the Pancora, and then we can construct the constraint to do the feature association, and then you can do optimization to do from the gradient descent to from the initial guess to the optimal solution. So also still, okay, unrelated motion can be obtained. And for the feature extraction, you can use several methods like the normal distribution transform and to the edge feature detection, for example, based on the long algorithm, and this is the NDT. So these two methods are currently the two most popular methods in the LiDAR science society. So the objective is here to find the representative features. So the second part is the feature association to get the feature to correspondence distances. So for example, the point to frame and the NDT is the point to distribution. So this is to find the same features and construct the constraint. So finally, based on the constraint, we can solve the optimization problem to estimate the transformation of the Pancora in two frames. So this is the key concept of the LiDAR lens. For example, if you look into the NDT, okay, the normal distribution transform. So a set of points you can obtain, okay, a set of points, for example, in here, the blue point. And the red point, it represents the Pancora in the next frame, okay, two consecutive frame of Pancora. So first we can do the NDT transform to transform those points into the distribution using a voxelization. In here, it's represented by a voxel. First, we can calculate the statistic properties of this voxel, for example, the covariance. The covariance can be represented by the mean. This is the mean, this is the point. The covariance can represent all the points inside the voxels are represented. For example, those features, okay, can be represented like this. Okay, this is the shape. For example, covariance, this is the long axis, this is the short axis. Okay, it represents different distributions of the points inside the voxel. So by doing the modeling, okay, we can calculate the cost function of the NDT based modeling. It's the same by transferring the point from current epoch to previous epoch to calculate the differences of the covariance. And okay, based on the cost, we can calculate the score and do optimization to get the state. So it's almost the same as the GPS least square. We can calculate the increment of the transformation based on the Gauss-Newton method. Okay, so it's iterative. So still due to a time limitation, I will not dig into the equations. Another method is to detect the pitch and the planar features. So different from the previous NDT, the NDT use all the points, and this one tries to estimate, try to extract the most representative features. For example, here, those are the H features. Those are the line features. Okay, located in a line, located within an H. So how does it extracted? Very straightforward. By calculating the smoothness. For example, in here, calculate the smoothness between this point and its neighboring features. Okay, let's say smoothness calculation. So based on, for example, from 50 features, from 50 points, we can calculate the smoothness. For example, if the smoothness is larger than this one, it should be an H feature. And if the planar feature, the smoothness should be pretty small. Okay, this is the key concept to extract the planar and H features. So based on this, we can, for example, for the H features, here is a feature, we can calculate the distance from a point to a line by doing the projection. So let's see the residuals. The several key steps is to first find the nearest H features. For example, H points. For example, in here, this can be calculated by easily project this point to the non-vector of this line. So therefore, we can calculate distance. And for the planar features, first we need to find the nearest eight planar features. So in here, for example, here is a plane. By projecting this point through this non-vector of the plane, we can calculate the distance from the planar feature to the plane. Okay, let's see the residuals for the H and for the planar. And finally, by combining the two kinds of residuals, we can solve the optimization problem to get the transformation. So let's see the key concept of the H and planar feature. So if you make a comparison, we can find the most important thing is to extract the features. And then we need to construct the constraints based on all those features and solve it. We can get the solution, the transformation. For example, in here, we get the features based on the covariance and construct the constraints and solve it. We get a transformation. And then we calculate the residuals and solve it. We get a transformation from like that. Okay, the last part about the degeneration. So sometimes if you get into dense urbans, the feature can be very limited. For example, in the sparse environment and the transformation, let's say what you want to estimate, and let's say the observation function, and the observation function is based on state and observation, and let's say the map. And sometimes, if the feature is quite sparse, so what will happen? So for example, if you're going to get like 10 features, 10 planar features, okay, let's take a look. Let's see how we solve it. So let's say the state we want to estimate. We first have the observation function together with the noise. Okay, we can solve it by solving optimization function. Let's say the residuals. So through the linearization of the observation functions, we can have its Jacobian matrix. And based on Jacobian matrix J of the H, we can do the least square estimation simultaneously to get the X within this observation function. So let's say how we achieve this. So for example, for the planar feature, okay, we can calculate the Jacobian based on the chain rule. For example, in here, we can calculate the Jacobian matrix of the H corresponding to the X. So based on the chain rule, first we can calculate the Jacobian of G. The G is corresponding to this term, the transformation. And then we can calculate the chain rule derivatives of the state. So this is the chain rule. And because this term is not related to the rotation, so the Jacobian term is 1. And finally, we can get the Jacobian term of this one. So due to the time limitation, if you get interested, please refer to this recent paper about the derivation of the Jacobian matrix. Okay, the almost last term. Okay, if we get this Jacobian calculation, we construct, okay, each feature observation into a matrix form. For example, let's say the state. For each feature, it's going to correlate with your state to get the constraint. And second feature, last feature, we get a lot of constraint to get this Jacobian matrix. Okay, for example, if we only get the 3 matrix, okay, rank of this Jacobian matrix is going to be 3. Okay, we get a set of features, we get this one, and all those features constrain the state can be also obtained from the Jacobian matrix. Okay, we do the SVD decomposition, we can get the eigenvalues, which is corresponding to how those states are corresponding constraints or state estimation from different directions. Okay, those are eigenvectors transpose, those are eigenvalues. So typically, if the eigenvalues is larger, it means in this direction, the constraint is better. So this is the key concept of the eigenvalues, the connection between the eigenvalues and the state estimation. So for example, in here, this is the case with dense features. The constraints are definitely better. So in here, only very limited features are obtained. So the constraints are weaker. So it means the eigenvalues in this diagonal matrix is smaller. Okay, this can lead to like the degeneration. For example, if the minimum eigenvalues within the 6 eigenvalues are smaller than a given threshold, sometimes we call this is the degeneration cases. So this is the example. For example, if you use a LiDAR preliminary feature as an example, this is the number of features we use. For example, from typical value, it's about 500, and this is the eigenvalues in the 3 direction. This the field of view of the LiDAR is usually very small in the vertical direction. For example, the mechanical LiDAR, it should be like 15 degrees vertically on the positive term and minus for the negative term. So it's 30 degrees. So as a result, usually the z-axis, the eigenvalue for the z-axis is usually very small. So in here, the z direction usually tend to degenerate. So this rotation, this is the eigenvalues for the x as a comparison with z is usually smaller than the one from the x direction. So that's why usually the drift in the z direction for the LiDAR length is more distinct. So that's almost all for the slide. So sorry for the overtime. So feel free to raise any questions. So feel free to raise any questions.
Okay. I think it's now 30 past 10.
Okay, sorry, Professor.
No further question. I think maybe we can invite the third tutorial.
Yes, Dr. Law.
Okay.
Okay, thank you all.
Thank you very much. Thank you, Wen. Thank you, Wen. Okay.
If any questions, okay, feel free to contact me through email.
Question.
This is our website. Okay, thank you.
Thank you. Now we will invite Dr. Luo Yiran. Okay. Welcome.
Hi, hello. Can you hear me?
Yeah, we can hear. Okay. We can see your screen.
Okay, I will share it.
Okay.